Before we move on, any questions from the homework or from previous lectures? Anton, what do you have?
I had a question about 2.5 question 14, particularly the first and last subsection.
Give me a second. 2.5 14.
Yes.
Just want to make sure that you did get the answer correctly. So we are not talking about different question here. Are you sure it's 14?
I'm pretty sure, yes. Particularly the first one and last one, I didn't really understand why they were.
Let me share my screen. Okay, let's talk about problem 14. Okay, find the graph of, can everybody see my screen? Okay, find the graph of G. State whether or not G is continuous. Enter yes, it's yes, and this is no. Okay. At -4, is it continuous? Technically, it should be left continuous. Sorry, right continuous. At -4, right? So it's not continuous. X equal to -2. Clearly, it's not continuous because we have a jump discontinuity. X equal to 0, it is continuous. I don't see a hole. I don't see anything. And your function value is exactly the same as the limit. Number 4, there is a vertical asymptote, so not continuous. Number 5, 4. Oh, what I just said, number 4 is actually number 5. Number 4 is x2. Here's a jump, so nice. 6, there's a jump. Okay. 7, x equal to 8. It's not continuous.
All right. Aren't the first and last ones? Aren't those the limits and the function at that, or the y output at that input?
Yeah. So let me draw that. Let's figure out this. Yeah. All right, let me share this. Okay, so our question narrows down to here. Question is this one continuous? Right? And also, if you have a circle here, is this one continuous? Is that a question, right?
Yeah.
Now, here's the thing. Technically, we would need this. And for this one, you don't have FA. So clearly, this is not continuous, no matter what. For this one, it's kind of tricky. Technically, this one only have a right limit. The reason is not because the left is bad. The reason is the left is not even there. So it is correct to say this one is right continuous for this part. It's also okay to say it's continuous as long as you don't confuse yourself. That's why we say when we say continuous, we kind of say, hey, continuous on a closed interval. But what do you mean by continuous here? Because you only have one side continuity. Then we say, well, roughly, you know what I mean. Make sense here? Okay. So for our class, I will take both. You say it's continuous. I know totally your reason. You say it's not continuous. I also totally know your reason. Okay. Then the rest is try to figure out what WebWork wants. And sadly, there are two types of WebWork. Some WebWork treat this one as continuous, and some WebWork treat this one as not continuous. So just try something there. Okay. So in my class, you say this is continuous or not continuous, I will take both. As long as you know the reason why I take both. However, if you have a hole here, clearly it's not continuous because it's not even right continuous. because your function is missing. Okay. Does it answer your question? Awesome. Aaron, what do you have?
2.6 number 8, please.
2.68. Find the limit of this. All right. Let's try to see what we have. So the first thing we do is we plug in infinity. We cannot plug in infinity, but we roughly know what we mean, right? It's just like the top is infinity, the bottom is infinity because this is huge. So roughly, we have a indeterminate form. Now we know leading terms. All right. If I ask you to show the work, you need to do the work, but we're just looking for fill in the blank. So what's the leading term on the top? This. What's the leading term on the bottom? There's no choice because 1 doesn't really matter. Still okay? The rest is try to do the algebra and see what this gives you. Three square root of 18. Which is x 18 times 1/2. This gives you x to the 9 on the bottom. That should be the case. All right. Nick?
Yeah, 2.6 number 9.
Nick Kubanes, right?
Yeah.
2.6. There's no number 9. Do you mean the one after number 8? Which is 11?
Oh wait, I mean number 6, sorry.
Okay. Okay. I don't know how you made that, but okay. All right. Infinity. 20x minus x square root of x. 7x to the 5/2 minus 7x plus 7. Is this the one? Nick? Nick?
Yeah,
Is
that's
this?
right.
Oh,
That's
okay.
right.
Cool. So for this, and clearly we plug in, we have infinity over infinity. So the question is, what are the leading terms? I think a nice way to do it is try to write everything in standard form so you can compare the exponents. The part is this. Okay, so let's try to rewrite it. X squared times square root of x. Now you know x squared times x cubed is x to the 5th because you simply add these two. Therefore, we just add these two, which give me x to the 5/2. So on the top, we have 1 and this. This is the leading term. On the bottom, we have 1. We have x to 0 roughly. So together, the bottom should be this. That should be the answer. All right. Okay, just to keep in mind, usually I do things in this way. And that's what we do, right? We write the biggest term here, and then we run them in decent order. But in general, you may receive something messy. Okay. So if that confuses you, the first thing you want to do is probably just reorganize everything to make sure the biggest one, and then in descending order. Now it's easier to see. For this one, the leading term is hidden actually in the second term. In general, there is no guarantee how you receive the original data. So maybe you want to do some process yourself before you do anything. Okay. Other questions from homework? All right. Cool. So limits are done. We know how to do this. We know how to do this. Now we want to go back to where originally we started. I would put 2.7 and 2.8 together in the book. Okay. And then we will talk about derivatives and the rate of change. The first one is derivatives. All right, this was what we have. We say we want to say the changing rate. What we do is we do a change in y, we do a change in x. An example you can think about is we say we have the change in location, and then we have a change in time. That gives us the changing rate of the location with respect to the time. Okay, this is just a more general form of saying it. Then we calculate this changing rate. What we receive is going to be an average changing rate, just as we receive an average velocity if we do this. Okay. After that, what we do is we let the changes goes to 0. Then your average become instantaneous. That's our principle from the beginning. To put words into formula, this is what we got for the changing rate. Which corresponding to a graph, which basically means you went from A to A plus H. Your graph changed from here to this height. Then you quantify how much you changed in Y. You quantify how much you changed in X. Then you use this change divided by this change. That's your changing rate. That is what this formula says. Finally, when you finish, you let H goes to 0. This point become closer and closer to this point, and eventually you will receive the instantaneous changing rate. Sounds good? All right. Now, judging by the graph, we have a second conclusion. Basically, this over that is nothing but the slope of a secant line, which is given by this. That's the average rate of change. Totally makes sense. Now what you do is you let this point to go closer and closer to this one, secant line, become a tangent line. Which means eventually this point move all the way to overlap with this one, and then your changing rate will be this. Okay. So derivative, which is the changing rate, equals the slope of the tangent line. And they're talking about the same thing. Still okay? All right. Now we have a third way of doing this. This is nothing new. Basically, we have a formula which somebody prefer to use. That is the formula of this. I'm not going to make a big deal of this. I just want to show you. This one basically is the same formula as what we did before. So feel free to use whichever you prefer. Let us draw two graphs. Then we will show they're actually talking about the same thing. This we're familiar. This is A. This is A plus H. This is H. This is fx plus H minus fa. fa plus H. Okay, so we're looking for the rate of this line. Now, of course, the formula on the left does exactly the same thing, except for they name things a little bit differently. They name this one A, but instead of calling this one A plus H, they call it X. Okay, compared to what we have here, they just call it X. Then this is nothing but fx minus fa, which is the same as fa plus h minus a. Okay, and this, before we call it h, now we just call it x minus a. So can you see they are exactly the same formula, just different names? Okay. Cool. So that's it. That's the definition of derivative. The derivative of fx at x equal to a is given by two formulas, which are actually the same formula. It is the changing rate at x equal to a. It is also the slope of the tangent line at x equal to a. Sounds good? That basically means next time if I ask you what is the changing rate, or what is the slope of the tangent line, or what is the derivative of fx, I'm asking exactly the same thing. The way to compute them are exactly the same because they basically mean the same thing. Okay? Let's try some examples. Let's start with the easy one. Find the derivative of y equals x squared at x equal 2. Reflect. We just said it. That means you just need to compute this. Or you just need to compute this. And you should receive the same answer. Okay. This is the first time we do it, so I'm going to do it in both ways to just let you see the difference. Okay. Later in our class, you can pick whichever you want because you really just receive the same answer. Sounds good? So just for this time, I'm going to do it both ways. You just need to do it for one way later, whichever way you prefer. Okay, so let's start with way 1. All I need to do is just take this one. I know A, right? A is 2. And then just do the computation. 2 plus h square minus 2 square divided by h, which is limit. Actually, we can stop here. After the setup, what do you see? You see a broken iPad. Oh, it's better here. Oh, okay, it's still there. Oh, good, good, good. Okay. Can you see this is nothing but a webwork from 2.3? And if you can handle that, you can handle this. Limit, plug in 0, which is 0 over 0. There is a hole. Then let's cancel some terms by using algebra. Can you plug in 0 now? The answer is 2. What did I say? Something is wrong. What did I do wrong? Here. This should be a 4. The answer should be 4. Sounds good? Everything for the last month is for us to be able to do this. Okay, finally, we were able to do it. So good news. All right. Let's try to do it the other way. Remember, A is 2. So fx, f2, x minus 2. What's the limit? There's a hole. Again, it becomes one of the webwork. Plug in 2. You got 2 plus 2, which is 4. Aaron.
Why do you square the fx minus f2? It's like the first one to the second one. Why do you square the top part?
From here to here, right?
Yes.
Okay. I'm not squaring. What I was doing is I'm doing fx equal to x squared. The f2 equals 2 squared.
Okay.
So I'm not squaring it. What I did is I plugged in both things into the fx, and fx this time happened to become x squared.
Okay.
Yeah, good. Okay. Is this example clear? From now on, every time I ask you for the derivative, pick one of the formula, finish the computation. The way to set it up should be easy. The harder part lies in how to do the limit, because we did all the web works. There are all kinds of random things can happen, right? But the setup should be easy. You can pick whichever formula you want. From now on in my lecture, I will focus on the formula 1. But if somehow you have a preference for formula 2, feel free to use it. Okay, I will take both as an answer. Find the changing rate of y equals 1 over x at x equal to 1. What is the changing rate? Well, let's draw it. What's the changing rate here? At least I can tell the changing rate is negative because it's decreasing going from here. Because it's decreasing. Okay. Can you tell more? We cannot. It may be -2, it may be -3, it may be negative, I don't know, 1.5. We really have to go to the calculation. Okay, so let's do the computation. Changing rate is the same as the derivative, and the derivative is this formula. 1 plus h minus f1 divided by h, a equals 1. Now you can see I'm not squaring it. It really depends on which formula you have. This time it's 1 over x. Then I have to do this. Can everybody see it's 0 over 0 case if you plug in 0? Then we have to cancel the terms. There's no conjugate, no anything, so probably common denominator, combine fractions. This is 1 minus h on the top. Negative h, 1 plus h, divide by h again. If you don't like this, you can change it to times 1 over h, which is the same as dividing by h. Plug in 0, no trouble. Great. Is it negative? As we expected. Moreover, this time we know firmly how negative. This red line here, 45 degree going down because the slope is -1. Cool. This one all right? It's just web work after web work. Number 3, find the equation of the tangent line of y equals this at x equals 1. Do you know the graph? It's the inverse of a parabola. That means take the parabola, flip it. 1, 1. You're looking for this line. All right. To find a line, what do you need? What information do you need? You need a point, you need a slope, and that's it. Okay. Do you know the point already? Yeah, it's x equal to 1. And your y is square root of 1, which is 1. You just need a slope. Now, how do you find the slope of a tangent line? That's the derivative. Then can you see that we're just doing the limit again? Square root. Adam.
So are you doing h goes to 0 because the points are like the same thing technically?
Can you be more specific? Which points are the same thing?
Well, the point becomes like 1 point. Is that why h is going to 0?
Let me just clarify what you're trying to say. Make sure that I'm answering it correctly. In general, you're doing this for a second line, right?
Yeah.
But you're not happy because eventually it's not what happens here. It's what happened here and a little bit moment after. What you want is what happens here. Therefore, this point should be closer and closer and closer, and eventually these two become the same. That's exactly letting h become 0. And your h is actually how long this is.
So when you take the derivative, it should always be 0 as h goes to 0? Okay.
Because you're looking for tangent line, yeah.
Thank you.
Are we good so far? How to find the limit? Zach?
Multiply by the conjugate.
Multiply by the conjugate. See, we're getting better. We know how to handle all the cases so far. Okay, limit. Square the first. Square the second. 1 plus h minus 1. The top is just h. 1 over 1 plus 0 plus 1, which is 1/2. Therefore, tangent line I have the slope, I have a 0.11. This is the point slope form. If I don't say it in the original problem, I will take any form you have. You can do point slope. You can do slope intercept, whichever way you prefer. I will take all of them. Okay. Does everything make sense so far? We did everything before. To find the definition of what Adam just said, we let h goes to 0. The only difficulty before was we don't know how to let h go to 0. We don't know what limit is, but now we know how to calculate it. So before we get stuck here, once we see this, now we can proceed further by timing the conjugate, by removing the hole, by doing the vertical asymptote, whatever case we have. Okay? Then we're all set for derivative. From now on, every time I ask you to do the derivative, at least you should be able to proceed to this step. After that, it's not even a derivative. It's just finding a limit problem. The difficulty is sometimes you got an easy one, sometimes you got a hard one, and very possible you will have an impossible one. Still okay? But at least we should be confident before this step. After that, it depends. Hard, easy, we don't know. Okay, that is good. Nick.
I'm just kind of confused how you canceled everything out, like where everything's crossed out. Like, how come there's an h in the numerator?
Oh, I see. Let me write the original thing. Are you okay with this step?
Yeah.
Okay. After that, can you see this 1 and this 1 cancel out?
Mm-hmm.
That leaves you a h on the top, right?
Okay.
And then the h and h cancel out.
Okay.
Yep.
Thank you.
This is a 1 here. Cool. Now let's talk about the second case. I'm going to ask you, what's the changing rate of y equals x at x equal to 1? Let's do it. Cancel, cancel. Cancel, cancel. Plug in 0. It's 2. Easy. Now question. What's the changing rate of y equals x squared at x equal to 2? What do you do? Equals 4. Make sense so far? Now, I'm going to ask you, what is the derivative of y equals x squared at x equal to 3? What do? You say you must be kidding me. Okay, I have to repeat that thing again and again and again. That's not good. I'm pissed, right? Do you have a better way of doing this? If I'm going to say, hey, I'm going to ask you actually for 10 points, for the same function, y equals x squared, I'm going to ask you what's the changing rate at 1, 2, 3, 4, 5, 6, all the way to 10. Do you have a better way of doing this? How do you do that? Well, instead of finding the changing rate at a certain point, I find it at a very general x. I just keep the x there. We pretend x is 1, or maybe 2, or maybe 3. But let's just pretend it's nothing but general. So let's change the way you ask stuff. Find the derivative not for x equal to 1, for any x. That's step 1. After that, if you want to know what happens at 1, you just plug in x equal to 1. If you want to know what happens at 3, you just plug in x equal to 3. Is the logic clear? Cool. Then let's try that. Is it impossible or is it actually doable? So this time, we do the same thing. Before we put a 1 here or 2 here, depends on which point. This time we put a general x. It's not as easy as before, because before we have numbers. But it's not impossible either. Let's just keep the x there. Cancel, cancel. Cancel, cancel. 2x. Make sense so far? This one works for which number? This one works for any number. What's the changing rate at 1? That's going to be 2. What's the changing rate at 12? That's going to be 24. What's the changing rate of x squared at 36? That's going to be 72. You can just keep going. And you don't have to do this again, and again. Instead, you just do it for once. And then you plug in different numbers. Okay? This is actually a very valid point in real life. You have some fx, and you want f changing rate. At a. What do? You do this. Which is great. Problem, every time you change a, you redo this. Sounds good? Another way of doing it, well, you first go this way. You do it. But you do it for any x. You don't fix a certain number. You just do it. When you finish, what do you get? You get something with an x inside. Still okay? After that, you just try one thing. That is plug in a. Now, if you change a, what happened? Well, if you change a, you just plug in a different a. You redo this. Okay. Instead of redoing the whole thing, you just redo the last part. And as we showed just now, the last part is easy. For this part, you only have to do it for once. And that once works for all a from now on. Sounds good? From here, you can see doing it with x is a little bit more trouble, but it's going to be worth it. As long as you do more than 1 point, it's going to be totally worth it. Okay? We give this a name. We call it derivative. But this derivative actually gives you the derivative at any single x. So this is actually a derivative with an x inside. We call it derivative function with x. The definition is straightforward. That's just this. What we just did is we calculated x squared, if you take the derivative, is equal to 2x. Maybe some other stuff later, sin x, you may have some other derivatives, but whatever way, you just finish it, you got a function. Now what's the change rate at a certain point? You just plug in the point. That's why this is a function. Sounds good? Cool. Just to make sure that we get the right idea. This is actually a prime sign. So this is read as f prime x, which stands for the derivative function of a function. Okay. That's the first thing. Derivative function. It tells all the information about the changing rate of f. Everywhere, not just at one point. Sounds good. Let's try to play a game. Let's try to see how fast we can build a impression of this. What I'm going to do is I'm going to draw the function here and the derivative of the function here. Our job is knowing one and try to think about what the other one looks like. Okay? First one, if this is fx, what do you think the graph of f prime x will be? What's the changing rate here? No change, 0. What's the changing rate here? No change, 0. Everywhere, 0. Do you know how to draw that function? Well, it's just 0 everywhere. That's my f prime x. Good. What's the changing rate here? A number. Maybe 1, maybe 1.5, depending on how well I can draw it, right? But it's a number. Number 2, is it positive or negative? Positive because it's increasing. What about here? The same number. What about here? The same number. Can you see this one has a constant changing rate? Okay, therefore it's still a horizontal line, but this time it's above because it's positive all the time. Similarly, I think you can get the idea. What's the derivative? It's going to be a constant, always negative. Still okay? Now remember, this tells you the relationship between the original one and the derivative, the changing rate. If this is your location, then this is your velocity. Make sense so far? This one just tells you if you drive at a constant velocity, then your change of location should be linear. You double the time, you double the distance because you're driving at a constant speed. Right? 2 hours is definitely twice as 1 hour because you're not changing your speed. Great. What if the derivative looked like this? Anton?
Oh, kind of like in the last example, initially it'd be like a parabola.
Parabola. Can you justify why?
Well, when we did in the last one with x squared, it turned out the derivative was 2x.
Oh, okay. So you basically say you matched. What if I change this one to to this?
It would still be a parabola.
Parabola. What if I change this one to this?
Definitely not a parabola.
But roughly, what's the idea here? If you think about it, right? What I'm saying are two things. Number one, the changing rate is positive, so definitely this one is going up. Second, how do you go up? Well, technically, you drive faster and faster and faster, or your changing rate become bigger and bigger and bigger. So when you do go up, this is a constant rate, but then you do have two options. You can either go up in this way, or you can go up in this way, right? What's the difference? Can you see that for this one? As you go, you drive faster and faster and faster. That means your derivative should be increasing. Instead, if you're going this way, that means you're driving slower and slower and slower. That means your derivative should be decreasing. Therefore, this should be a parabola type, simply because you're driving faster and faster. So what do you think the derivative will look like if the thing is like this? Number one, your derivative should be decreasing. Number two, even though it's decreasing, it should be always positive, at least. So roughly, your derivative is going to be like this. Cool. Let me draw a circle. My drawing is bad. Well, actually, not too bad. Half circle. Okay. What do you think the derivative will look like? Jordan?
So what I'm thinking is at the very middle, it's gonna have to be at 0 because you're like
because of this.
Your slope's gonna be 0.
Well, okay. Let me try to draw it straight. All right. Then before that,
And then on the left side, you're like still increasing, and then after that, you're decreasing,
So above and below.
pretty much.
And then you're increasing at a faster rate or lower rate on the left. Are you going faster and faster or slower and slower?
Oh, you're slowing down.
So we should be going down. Okay. Then we're driving in the other direction. We're decreasing, but decreasing at a faster and faster rate. So that should be like this. Okay. What's the changing rate here? My drawing is bad, but for half circle, what's the changing rate here? It's going to be negative. It's going to be negative. And because it's vertical, it's negative infinity. Can everybody see that? What's your slope of a vertical line? That's going to be infinity. So actually at here, you should have infinity. Then at here, you should have positive infinity together. Roughly, the thing should look like this. What you said was basically correct, except for in the end, actually we reach the extreme. That should be the derivative of a circle. Do you get a rough feeling like the relationship between the function and the derivative of the function? Go back, try something yourself, draw some easy functions, then try to draw the derivative, then draw some easy derivatives and try to recover the functions. We will do more tomorrow. Okay? That's all for today. If you have questions, stay.